Welcome back, everyone. Today we talk about section 1.7, the mixture problem. And this is, as I alluded to in the last video, an application of the technique that we learned in section 1.6, which is the integrating factor. Okay, so this is why we learned the integrating factor. Okay, more or less the problems that we're going to look at today all have the same basic setup. Okay, and it goes a little bit like this. A tank initially contains 600 liters of a solution in which there's 1,500 grams of a dissolved chemical. We can call it salt. A solution containing 5 grams per liter of salt flows into the tank, that's this coming here, at a rate of 6 liters per minute. The mixture is well stirred and exits at 3 liters per minute. Determine the concentration of salt in the tank after an hour. Okay. And the components of the problem will change, the numbers will change, you will have different punchlines to the problem. This one says, tell us the concentration of the salt in the tank after 1 hour. Another problem can say, tell us how many, the quantity of the amount of salt in the tank after 1 hour. It can say, tell us the concentration of salt in the tank when it's half full, or 10 minutes after it's half full. There's all different versions of it, but it basically goes a little bit like that. Okay, now because these problems are very consistent, there's going to be some measurements that are super important. One is the mass of the salt at any given time, so the mass of the salt that's actually in the tank. Okay, the volume of the liquid that's in the tank, so the salt, and I'm calling it salt for today's lecture. Could be any chemical. Okay, so the volume of the liquid in the tank, M naught is the initial mass of the salt in the tank. V naught is the initial volume of the solution in the tank. Rn is the rate at which liquid is flowing into the tank. R out is the rate at which it's flowing out. Cin and C out are the concentrations of the chemical in the liquid as it goes in and as it goes out. Okay, so those are what each of those symbols will represent. They all play a role in solving this problem. So things to keep in mind. One is you need to find the differential equation that models the situation. And we'll use it by looking at the conservation of mass. Okay, the rate of change of mass, dm dt, is the mass rate in minus the mass rate out. Okay, so we can look at something simple like the dimensions. Okay, you have a solution going into the tank at, what was it? 6 liters per minute. Sorry, 6 liters per minute. And the concentration going in the tank was 0.5. Sorry, I'm having a difficult time tonight. 0.5 grams per liter. So if you have the solution going in at 6 liters per minute at half a gram per liter, the units liters cancel, and you're left with 3 grams per minute. And what is that representing? Well, grams is a measure of mass, and minutes is a measure of time. So what this is representing is the change in mass over the change in time. And if we look at it at an instant, that's dm dt. Okay, so as you look at this, dm dt is going to be the rate, the change in mass going in minus the change in mass going out. The fluid flowing out of the tank has the same concentration as the fluid in the tank. So this chemical salt is coming in here, it's instantaneously mixed, so whatever the concentration of salt is in the tank, that's the same concentration as the solution coming out of the tank, but which can be different than the concentration that's going in. Okay, so what that means is the concentration going out is mass, the amount of salt in the tank, divided by volume, the amount of fluid in the tank. So C out is always going to be M over V. The volume of the solution in the tank depends on a couple things, okay? The flow rate in and the flow rate out, as well as the initial volume of the solution in the tank. So the volume of fluid in the tank is going to be the initial amount plus T times the rate at which it goes in minus the rate at which it goes out. Okay, and last thing you want to keep in mind is that you're going to come up, when you plug all these components into dMdt, with a differential equation. Okay, and you're going to use you're going to solve the differential equation predominantly using the not integration by parts, the integrating factor. You'll use the integrating factor to solve that differential equation to come up with the mass of the solution, the amount of salt in the tank at any given time. And once you find mass as a function of time, you're able to solve whatever question the problem is asking you. Okay. All right, so there's many steps to the problems. Okay, once you thoroughly understand a problem from beginning to end, you're going to find these problems somewhat repetitive and maybe even boring. Okay, but until you understand each and every one of the steps, you might find them all impossible, and that's really what math is. Okay, as soon as you know the solution to a problem, it seems very easy, but until you know the solution to the problem, it's by definition impossible for you to do it. So there we go. Let's get started. Actually, let's start with the problem that I assigned you. Where did it go? All right. The tank initially contains 600 liters of a solution. Okay, so that means V naught is 600 liters, in which there's 1,500 grams of dissolved chemical salt. So M naught is 1,500 grams. A solution containing 5 grams per liter of salt, so that's the concentration flows into, so that's concentration going in, that's 5 grams per liter, into the tank at a rate, so Rn is 6 liters per minute. The mixture is well stirred and exits at 3 liters per minute. Okay, so what is the concentration going out? Well, it's the amount of salt in the tank divided by the volume of the tank. This will always be true. Okay. I should probably say almost always. I can't think of an instance where it isn't, but I just want to cover myself. And exits at a rate of 3 liters per minute. Okay, determine the concentration of the salt in the tank after 1 hour. Okay, so the concentration after 1 hour. So I'll write that into words. We want the concentration in the tank after 60 minutes. Now, why did I change to minutes? Well, because the units of R in and R out are in minutes. So our function M of t should be in minutes. And the concentration after 60 minutes, so C of 60, is going to be the amount of salt in the tank after 60 minutes divided by the volume of the tank after 60 minutes. So I need M of 60 and I need V of 60. Okay, so those are two things that I will want to keep in mind. All right. V of 60 I can actually come up with already. Okay, because I know there's 600 liters in the tank initially. Okay. The rate at which fluid goes in the tank is 6 liters per minute. The rate at which it goes out is 3 liters per minute. So that means each minute I'm increasing the amount of solution in the tank by 3 liters per minute. And I want it after 60 minutes. So I can start off with that equation for V of 60, and you can see it closely models what I have for V of t. V of t is initial 600 plus t times. We know this is going to be 60 minutes times the difference between rate in and rate out. Okay, so that's good. Setting up the differential equation goes like this. We know that dm dt, so I'm put it in red to grab your attention. dm dt is going to be equal to the concentration in, so the concentration is 5 grams per liter, so that's 5, times Rn, that's 6, minus C out, that's M over V. And you should confirm why that makes sense, why everything else can be numerical and this has to be symbolic. Because as time changes, the mass of salt in the tank will change, okay? And the volume of solution in the tank will change as well, okay? Because there's no guarantee that the concentration that's presently in the tank is just as salty as the solution that's flowing into the tank. So we get M over V times R out. What's R out? In this case, it's 3. Okay, and there's our differential equation. dm dt equals 30 minus 3 over V times M. Okay, we don't want to leave this as V. I probably should have caught that in the last step. 3 over what? Well, our formula for V. That's 600 plus T times 6 minus 3. That's going to be all times M. So there is the differential equation I'm going to solve. So let's solve it. dm dt, just writing it in a more simplified form. Okay, dm dt is equal to 30 minus 3 over 600 plus 3t times m. Now, if you remember the format of the integrating factor, I needed it to be of the form y prime plus, what did I call this one? P of x, y equals q of x. Okay, so here, y is my dependent variable, x is my independent variable. Here, m is my dependent variable, t is my independent variable. So, dm dt is playing the role of y prime, so let's call this m prime. And I want all the terms that involve m on the left-hand side of the equation, things that involve t on the right-hand side of the equation. So this term right here involves an m, so I'll add that over. So we get 3 over 600 plus 3t times m equals what? 30. So there are no x's on this side of the equation, but that's not a problem. So now the differential equation is of the form that we're familiar using. The integrating factor, change colors for this, the integrating factor is going to be e to the integral of this term out in front. So it's 3 over 600 plus 3t dt. So as you can see here, the derivative of 600 plus 3t is 0 plus 3, so that's 3. Happens to be in the numerator, so this is a natural log integral. So it's the natural log of the absolute value of 600 plus 3t. The e and the natural log kill each other off, and you're left with 600 plus 3t as your integrating factor. So you take that term and you multiply both sides by 600 plus 3t. So on the left-hand side, this now becomes 600 plus 3t times m prime plus the 600 plus 3t in red cancels the 600 plus 3t in green, so that's now 3m, and that equals, sure, well, let's distribute this through. So 600 times 30, what's that going to be? 6,000, it'd be 18,000 plus 90t. There we go. Hopefully that's the right move to make. Now the goal here is to have integrated correctly so that the left-hand side is the derivative of some product. That product will be the dependent variable m times what? 600 plus 3t. Okay, and we can double check that. The derivative of the first is m prime times the second, that's 600 plus 3t, plus the derivative of the second. So the derivative of 600 plus 3t is 3 times the first, which is m. And that's all equal to, again, 18,000 plus 90t. And now we get to integrate both sides with respect to t. So integrate this with respect to t, integrate this with respect to t. And what do we get? Well, this is m times 600 plus 3t equals 18,000t plus 45t squared plus a constant. Can't forget that constant. So now, dividing by 600 plus 3t, what do we get? We get 18,000t plus 45t squared over 600 plus 3t. Not convinced you couldn't simplify that a little bit. Not sure if that's the case or not. Might look into that. Plus c over 600 plus 3t. Okay, and maybe we should look into that just a little bit. There's a common factor of t that's in the numerator. Pull that out. If there were going to be any cancellation, you'd want it to cancel with 600 plus 3t. So that means I can take a 15t out of 45t squared and be left with a 3t. So let's see if I can pull 15t out of something. If I were to divide 18,000 divided by 15. I got that to be 1,200. Oh, bummer. Make sure I did all my computations right. Oops. 30 times 600 is 18,000. All right, everything looks fine. I was hoping that I could get some sort of cancellation, but it didn't work. All right, and that's my formula for the mass of the salt in the tank at any given time. So now, go back to the top here. Okay, simplifying the bottom, that's 3 times 60. 3 times 60 is 180, so that's 780 liters in the tank. And I need to know the mass of the salt in the tank at time equals 60. Well, I can't quite find that yet. Okay, because this right here is a general solution. Hence the plus C right there. I need a particular solution. I need the C that gives me an initial amount of salt to be 1,500 grams. So let's plug that in. So when time is 0, I need to have M be 1,500. So that's 0 plus 0 is 0 over 600 plus 3t, 0 over 600, plus C over 600. So C over 600 is equal to 1,500. So what does that tell you that C is? 1,500 times 600 is 900,000. All right. So our particular solution is 18,000 T plus 45T squared over 600 plus 3T plus 900,000 over 600 plus 3T. Why I left that is two different fractions added together when they both have the same denominator. Your guess is as good as mine. I probably shouldn't have done that. Okay, so what's M of 60? Okay, so 18,000 times T, so 18,000 times 60 is a big number. 1080, 1, 2, 3, so 1,080,000 plus 60 times 60 times 45, that's 162,000.